Hello, my name's Dan and welcome back to the channel. In this video I'm going to cover an end-to-end narrowband imaging project. So we're going to talk about target choice, data acquisition, processing and production of the final image. So let's sit down, have a chat about the target I've picked and why, and what even is narrowband imaging, and why should you bother with it. So let's get started and jump right in. We are joined by my furry assistant Bruce. He will be snoozing away. Hopefully he won't be snoring, but he won't mind us having a little chat about astrophotography. Put him to sleep. Anyway, the target for this project is the Tulip Nebula, or specifically the region around the Tulip Nebula. The Tulip Nebula itself is an emission nebula in the constellation Cygnus, and in the summer the Cygnus constellation comes up nice and high throughout the summer here in the UK. It's up for most of the night, reaches the zenith pretty much as well, like into the later months. So it's like perfect for a good long stretch of for a narrowband project. The nights are short as well in the summer in the UK, so I imagine this project will take a while. But if you want good results, you've got to put the effort in, right? The reason why I've picked the Tulip Nebula is because it's always quite difficult to select a target for a new project. But I use resources like Stellarium on the PC and Astrobin in particular to put in. I've got the telescope here, you can just about see it. I put in my equipment and I see what other images people are taking with similar equipment, so you can get a feel for what does or doesn't work with the setup you have. And the Tulip Nebula is sort of rarely imaged with this setup, but they usually the images come out really nice. And I actually recently purchased this book, the Astrophotography Sky Atlas by Charles Bracken. Apologies if I've mispronounced the name, but it is a fantastic resource for finding all sorts. I mean, as you can imagine, it's just star chart after star chart. Lots of maps, lots of reference tables as well for coordinates and brightness values. But having a look at the sort of Cygnus region, you see here all this dark color. This is sort of representing the sort of dust and the interstellar medium, the ISM as it's called, just a fancy word for stuff in between all the stars. And the Cygnus region is very busy. We've got the Veil Nebula complex, the Crescent Nebula, the Propeller Nebula, the Seda region. It's a busy area. Always makes for nice imaging projects. But I haven't done the Tulip Nebula before, and I just love how other people's pictures turn out on Astrobin, as I mentioned. And the Tulip Nebula is an emission nebula, which makes it perfect for narrowband imaging. So what is narrowband imaging? Broadly speaking, objects in space emit on a broadband sort of spectrum. So the electromagnetic spectrum, i.e. light, ranges all sorts of wavelengths from tiny values down at the gamma ray end to extremely long values like hundreds, thousands of meters in wavelength down at the radio wave end. Now right in the middle is the visible light spectrum, the light that our eyes have naturally evolved to pick up on, and obviously we're going to be capturing that using this monochrome camera here. But being monochrome, it can't capture the colors, so the light will come down into the objective lens of the telescope, go through the lenses, through the field flattener, and then ultimately end up passing through this filter wheel before it gets to the camera. And in here I have 7 filters: a luminance, a red, green, blue, and then I also have some narrowband filters, which I'll cover in just a second. But for broadband objects that emit light across the large portion of the visible spectrum, just your reds, your oranges, your yellows and blues, not so much greens, but there are filters in here to collect light that covers those red wavelengths, but that is quite a broad generic term there, red wavelengths. It covers sort of values down, I don't know, perhaps between 500 maybe that's a bit generous, 500 to 680 odd nanometers. That's sort of the red color. But yes, with emission nebulae and narrowband targets, what that means is that they emit light on a very narrow portion of that visible spectrum. So in here, I have 3 narrowband filters, ones that cover hydrogen, sulfur, and oxygen. Now this is what a narrowband filter looks like. This is a 2-inch threaded narrowband filter. And as you can probably make out there, it's extremely reflective, which means it's blocking a lot of the light that's trying to make its way through that filter. You know, I think, well, what's the point of that? We're taking pictures of faint objects. Why make it more difficult for ourselves if we're blocking a lot of the light? However, that is the main point of narrowband imaging. So those nebulae, emission nebulae, for example, they are made up of clouds of primarily hydrogen, and there are other chemical elements in there like sulfur and oxygen. Now the nearby stars emit all sorts of light in a broadband sort of range, and all that light impacts those chemical elements and molecules and atoms, excites them, energizes them, and they basically, in a nutshell, emit visible light as a way of cooling back down, relaxing back down to their natural state. And in doing so, that light that they emit is very specific in wavelength. So for hydrogen, I believe it's 656 nanometers. For sulfur, it's about 672 nanometers. And for oxygen, it's just under 500 nanometers. And those correlate to different colors. So that hydrogen color is a deep red. The sulfur is an even deeper red. And the oxygen color, that just under 500 nanometers, is like a teal blue sort of color. So these filters are designed to only let light through at those specific wavelengths. And there are different types. You can get ones that have a broader sort of window that let through 7 nanometers worth of light either side of those specific wavelengths. The ones I have in here are 3 nanometer wide, so they are quite narrow for narrowband filters. But that means the advantage there is that only light from the nebulae will make it through onto the camera sensor. So it's a great way to overcome the problems of light pollution in urban areas. This used to be better back in the day when we had sodium lamps here in the UK. They were a very specific yellow colour. However, the new white LEDs that they've put throughout the country are a bit more of a broadband sort of emitter. So a tiny portion could make its way through onto the camera. But in terms of how much light pollution is cut down, it's enormous. It gives you a huge advantage. It sort of almost guarantees that all the light this camera captures does in fact come from the nebulae or the object you're taking a picture of. So the plan there is to cycle through those narrowband filters, the hydrogen, sulfur and oxygen. So we'll map those in the processing to the red, green and blue colors to build a color image. Typically one that's very famous is called the Hubble Palette, where you map your sulfur colors to the red channel, your hydrogen to the green and your oxygen to the blue. And you build up some fantastic looking images. And that is exactly what we're going to do with this project. Being a narrowband project, it does mean that it's difficult to capture a lot of detail. So in one exposure, for example. So if you're doing a broadband sort of image, a lot of light will make it through. Those broadband filters let large portions of the visible spectrum through. So your camera gathers information effectively quicker. So with narrowband imaging, your single exposures will typically last 5 minutes and upwards of 5 minutes. I've seen people do 10-minute long exposures. Obviously, the longer you expose for, the better and steadier your guiding needs to be. So you need a good mount for the telescope. Thankfully, the setup I have here for guiding and my mount is quite good. I can rely on it to let me do 5-minute long exposures when I do narrowband projects. So that is going to be The goal on this is that I'm going to hope to achieve roughly 8 hours each of total exposure for hydrogen, sulfur and oxygen, and that should bring out some really nice details in the Tulip Nebula itself and the surrounding regions. So as I said, it's going to be a long project, but there's only one way to get started, right? It's to get this outside, get it all set up. It's very overcast and grey at the moment, but that is going to clear up later tonight. So yes, let's get cracking. Well, it's been 3 months now since I started this project on the Tulip Nebula and its surrounding regions, and in that time I've only had 7 nights worth of usable time under the stars with the telescope thanks to the British weather. That's just how it goes though. But I think hopefully you'll agree with me that in that time I managed to amass a total of just under 25 hours worth of total exposure time. I'll put a little breakdown here of how that's played out across those filters. And I don't think that's too bad going for British summertime, you know, on the Narrowband project, 25 hours worth. And you can see here, I did go back and get some natural red, green and blue sort of broadband data there. And the reason for that is I'll take the narrowband data, build a nice colour image from that in the Hubble Palette style, like I mentioned earlier. And I will apply the red, green and blue natural star colours on top of those. If you use the stars from your narrowband data, they can look a bit funky because of how we apply some color mapping there. There are tools to sort of overcome that. However, I quite like just gathering a small amount of data in comparison. It was only about half an hour in each filter, but building a nice color image of the natural stars. We can run it through some color calibration tools as well, but I think a narrowband nebula picture with natural stars on top is the way to go. I always like how they look. So yes, I did film the whole processing process of this picture, just sort of how we go through building the color image and calibrating things and what have you. However, the whole video would be about an hour long. So what I've done is I've chopped this into 2. Keep this video about the target and what is narrowband imaging. And then I'll pop a little card up here for the processing tutorial, which I'll publish next week. So if you're interested in seeing how I process this image, going from the stacked single images in hydrogen, sulfur and oxygen to the final Hubble Palette image and adding those natural colours in for the stars, then give that a watch. It is a bit long, but you know, building these images is a long process. So yeah. Let's jump over now to the PC there and just see what a narrowband image sort of looks like after stacking. So this was stacked in PixInsight using WBPP, weighted batch pre-processing. So that's just PixInsight's sort of script for, you know, averaging out all of those single exposures, building up the right signals for noise in those separate images, rejecting the outliers from satellites and things like that. So if we have a look here in the top left, we have sulfur, top right we have oxygen, and at the bottom we have hydrogen. Now you might think something's gone wrong because they're just black images. However, what's actually happening is all of our narrowband information is packed into a very narrow portion of the image's data. So what we need to do is sort of look into all that data and stretch that bit out where all that information is. And in the processing video I go through how to do this like properly, balancing all the levels, etc. However, in here we can just apply what's called an STF, a screen transfer function, to just sort of give us a preview of the data that's buried in the image. So whilst this looks black, if we apply the STF to it, you can see some detail starts to pop out here. So this being the sulfur channel, we can see that there's some dust and some actual detail and interest going on. And we can really have a look at, say, the Tulip Nebula here. It's quite bright in sulfur. or in comparison to the rest of the region. So that should bring us out some nice details. You can see it's quite noisy as well, which is to be expected from the sulfur channel. And if we have a look at oxygen, for example, not so much going on in this one compared to sulfur. However, that's usually the case. It does vary depending on the target. However, for this region, this is coming out quite nicely. We can see this nice bright area here, especially down in the bottom right. So that is the result of a Wolf-Rayet star. It's almost like a little shock wave. You can see the bow shock there. And the core of the Tulip Nebula is looking quite bright as well, which is to be expected. So that's very nice. And then if we look at hydrogen, which hopefully when we press this button, the screen transfer function, it will look great, which it does, in my opinion. Yeah, this is looking very nice. You can see a lot of detail here. And typically with narrowband imaging, your hydrogen sort of data is the cleanest, the brightest. It's got the best signal to noise ratio in there, purely because the nebulous region you're taking an image of is mainly comprised of hydrogen. So by far it's the most data you'll gather. So you can see here, like if we look at the tulip, it's just so much brighter than the others. It looks very good there. There's going to be a lot of detail we'll be able to pull out of this. Far less noise as well, which is nice to see. We can really see all this detail, all these dusty regions. That's going to bring out some nice contrast in the final image. In fact, let's make this a bit bigger. We can have a proper look at it there. That is quite nice. But as you can see, they are monochrome still. They are black and white. So in processing, this gets combined using channel combination and linear fit and things like that to balance out the sort of levels of the images. So that's covered in the processing video. However, in this one, I'm just going to leave you here with the monochrome images, but I will show you the final image that I have produced, and we'll have a closer look at it and talk about what's in it, because there's some really interesting stuff in there. Well, there's my final image of the Tulip Nebula and the surrounding dusty regions in the Cygnus constellation. I'm personally very happy with how this image turned out, and I hope you've enjoyed it as well. And I thought now would be a good chance to jump into the image and zoom in and have a look at some areas of particular interest. One in particular is up here in the top left, where there seems to be a bright blue bubble looking thing. So let's take a closer look, and what we're actually seeing here is a bright blue shock wave that's 130 light years across in diameter, generated by one star. And I'll pop a circle around the star so we know which one we're talking about. This star is called WR134, and that's not a very particularly interesting name, but the WR bit it stands for Wolf-Rayet. Now, Wolf-Rayet star is a particular type of star that's very uncommon. So we know roughly of 600 of them throughout the Milky Way out of a population of 100 to 400 billion stars. So they are very rare indeed, and they tend to be categorized by being very luminous. So this one in particular has 400,000 times the luminosity of our own sun. Very hot, and they have a slightly less rich percentage of hydrogen and slightly higher percentage of heavier elements like carbon and nitrogen. But this one in particular, through its luminosity and high temperature, it's been producing a very strong stellar wind. So over millions and billions of years, this has been producing this wind, pushing out against the interstellar medium, creating this bright blue shockwave that we're seeing that's very strong in that oxygen signal. So I'm really happy that this came out nicely in the image. And if we jump over now to the tulip itself and make our way across the middle of the image, I'm really happy as well with that. We've managed to pick out these high contrasting areas of it where these dark nebulae are sat against the bright blue sort of reflections and emissions from the hydrogen clouds. But the tulip itself is about 70 light years across and has a nice bright blue core, very strong in our oxygen signal. And I'm really happy with how the sort of dust lanes inside there have really created that nice contrast that we can see in the core there. And there is particularly one object that doesn't look very interesting just above it. It's this, I'll pop a circle around it. It's like this red purplish looking arc and doesn't look too interesting, but this is the result of something called Cygnus X1. Cygnus X1 was discovered in the early 70s, and to this day it's one of the brightest X-ray sources that we can detect from the Earth. And it was hypothesized that this was the first black hole that we could observe. Well, the effects we could observe and determine that this is indeed a black hole. And what this actually turned out to be is a binary system between a blue supergiant star and a black hole. So what that means, binary system, what that means is that they're just orbiting one another. Now the blue supergiant star itself is about 30 solar masses, so 30 times the mass of our sun, and the black hole is about 15 solar masses, but they are very close to one another. And the stellar wind from the blue supergiant means it's emitting this wind that's being picked up by the black hole. It's falling onto its accretion disk, getting very hot, very bright, and in doing so, some of that is deflected by the magnetic field of the black hole and creates these relativistic jets of particles. What this means is that it accelerates that matter that's falling onto the accretion disk and shoots it out from the top of the black hole perpendicular to the disk at relativistic speed, so very close to light speed. So crazy amounts of energy are involved in this. And what we're seeing here is the result of that jet impacting the interstellar medium, so all the dust and stuff around the Tulip Nebula area. So it doesn't look particularly interesting, but when you do a bit of research and you work out what this actually is, I think it's pretty mind-blowing that we've managed to pick this up. It's quite faint, but still it's come through quite nicely in the final image. So once again, that's my final picture of the Tulip Nebula. I hope you've enjoyed this video. I hope I haven't rambled on too much, and I hope you like having a little look around at the end there about what we're actually seeing in the image. So I'll wrap it up there. Thank you very much for watching, and if you go stargazing yourself, I wish you clear skies.